Hi, my name is Mr. Peck from Ideas Inc. School, and today we will be talking about the refraction of light. The refraction of light is the behavior of light as it enters mediums of different densities. The optical density of a medium affects the extent to which a substance is able to transmit visible light. There are two scenarios to consider. Number 1, when light enters a denser medium, it will slow down and bend towards the imaginary normal. Number 2, when light enters a less dense medium, it will speed up and bend away from the normal. Please refer to the diagram for a better understanding. Just like reflection, the incident ray originates from a light source. When the incident ray hits the boundary between air and water, the location is known as the point of incidence. From this point, an imaginary normal which is 90 degrees to the surface is drawn. Furthermore, two light rays emerge from the point of incidence. First, a reflected ray is produced due to the smooth and shiny nature of water. Second is another light ray known as the refracted ray going through the water body. The angle of incidence is measured from the incident ray to the normal, while the angle of refraction is found in between the refracted ray and the normal. The only exception to the above scenarios is when light strikes perpendicularly to the boundary between mediums. When that happens, light will pass straight through and no bending occurs. However, please note that although light does not bend, its speed still changes according to the medium that it enters. Let's take a look at a more detailed example to demonstrate the behavior of light going through multiple mediums. In this diagram, we have light passing through air, glass, water, and back out to air again. As light hits the boundary between air and glass, since glass is a denser medium than air, light will slow down when it enters and bend towards the normal. To showcase this better, we will produce an imaginary line that extends from the light ray that is traveling through air. This imaginary line will divide the following section into two key areas. The area nearer the normal is where light should be when it slows down and bends towards the normal. On the other hand, the outer area is where light will be if it speeds up and bends away from the normal. Since light is now traveling through a denser medium, it will pass through the area which is closer to the normal. Now the situation gets more interesting as light strikes the boundary between glass and water. Just like before, to showcase the refraction of light more clearly, we will produce an imaginary line that extends from the light ray that is traveling through glass. This line depicts the speed of light traveling through the glass medium. After that, another dotted line is drawn from the point of incidence. This new dotted line depicts the speed of light traveling through air, and please note that all light rays traveling through the same medium are parallel. So all rays of light traveling through air will form the same angle with the surface. Now we have two lines dividing the region into three sectors. Since light is traveling through water, which is a medium that is less dense than glass but at the same time denser than air, the relative speed of light will be faster than that of glass but slower as compared to air. As a result, the refracted light ray will appear in the area bounded by the two dotted lines that depict the speed of light in glass and air respectively. Finally, light will now strike the boundary between water and air. Because we have already established that light traveling through the same medium will have the same degree of bending and hence, same angle of refraction. When the light ray enters air again, it will emerge parallel to that of the original incident ray. In the next part of the chapter, we will demonstrate the refraction of light using ray diagrams. Let's observe the first example. Similar to what we have learned in reflection, we will be using Pekky's three-step method. First, we will draw the image which is located slightly above the object. Take note that since the image is virtual, we will be drawing it using dotted lines. And when using water as the medium, the object and image distance can be measured roughly using a 4:3 ratio. Second, we will draw light rays from the image to the observer's eye. Take note that the light rays beneath the water surface are imaginary, thus they are drawn using dotted lines. On the other hand, the light rays emerging from the water boundary are real, therefore they are drawn using solid lines. In the last step, we will connect solid light rays from the object to the point of incidence to complete the ray diagram. Let's take a look at another example for a better understanding. In this diagram, we have a straw that is partially inserted into a cup of water. Let's apply Pekky's three-step method again. First, we will draw the image appearing slightly above the object. Take note that since the straw is only partially submerged, the image that we observe will appear bent. Second, we will draw light rays from the image to the observer's eye. Please indicate correctly which lines are dotted and which are solid. Lastly, we will connect solid lines from the object to the point of incidence. But why does the image always appear to be in a higher position than the actual object? That is because our brains can only perceive light entering into our eyes in a straight line. Our eyes are unable to detect the bending of light due to it traveling from a denser to a less dense medium. As a result, light rays will appear to come from an image that is located above the object. In the next part of the chapter, we will be exploring how to calculate the refractive index of a medium and its applications. A refractive index of a medium is the ratio of the speed of light traveling through a vacuum compared to the speed of light in a specific medium. That is why, the greater the refractive index, the greater the optical density of the medium. Let's learn 3 ways to calculate it. First, we will be using Snell's law with the formula n equals sin I divided by sin r, where n stands for the refractive index, I stands for the angle of incidence, while r stands for the angle of refraction. Let's take a look at an example. An incident ray strikes the boundary between air and glass with an angle of incidence of 50 degrees. From the point of incidence emerges a refracted ray with an angle of refraction of 30 degrees. If we input these values into the formula sin I over sin r, we will have sin 50 degrees divided by sin 30 degrees, giving us a refractive index of about 1.53. Inversely, we now have an incident ray traveling from glass to air. To calculate, we must first take note that the refractive index of a medium must always be relative to vacuum or air. Therefore, when we input the angles into the formula, the angle used in the numerator has to be the angle of light traveling through air, and the denominator will then be the angle when light travels through the glass medium. Thus, we will divide sin 70 degrees by sin 50 degrees to obtain a refractive index of about 1.23. Regardless, a quick way to check is to ensure that the refractive index of a medium is always greater than the value of 1. Another way to calculate refractive index is to use the formula of real depth divided by apparent depth. The real depth is the actual distance from the boundary between two mediums to the actual object, while the apparent depth is the distance between the surface boundary and the virtual image. Let's take a look at how to apply the formula in this example. An observer is positioned about 1.3 meters above the water surface. If the observer sees an image 2.1 meters away and assuming that water has a refractive index of 1.33, can we calculate the real depth of the object? We calculate the apparent depth by subtracting 1.3 meters from 2.1 to obtain 0.8 meters. By using the formula of refractive index being the ratio of real depth over the apparent depth, we can conclude that the refractive index of 1.33 is equal to the real depth divided by the apparent depth of 0.8 meters. From here we can derive the real depth of about 1.06 meters. The last way to calculate the refractive index of a medium is to use the ratio between the speed of light traveling through a vacuum and the speed of light traveling through a different medium. In this simple example, given that the speed of light traveling through perspex is 2.01 times 10 to the power of 8 meters per second, can we calculate the refractive index of perspex? Since the speed of light traveling through a vacuum is a universal constant with a value of about 3 times 10 to the power of 8 meters per second. If we divide that value by the speed of light through perspex, we can derive the refractive index of about 1.49. In the last part of the chapter, we will be discussing about how the dispersion of light gives rise to an optical illusion known as a rainbow. As light crosses the boundary between air and glass, the speed of light slows down as it enters the denser medium. However, the different component colors that make up white light slows down to a different extent. For instance, red light has the longest wavelength of the visible spectrum, thus it travels the fastest through the glass prism. As a result, red light slows down the least and only bends slightly towards the normal. Violet light, on the other hand, has the shortest wavelength, thus it travels the slowest through the medium. This results in violet light having the greatest degree of bending and the smallest angle of refraction. Fun fact, no two people can observe the exact same rainbow. Even our left and right eyes will not see the same rainbow. Rainbows can only be observed from the ground during the early morning or late in the afternoon when the angle between the sun's rays and our eyes is between 40 to 42 degrees. And finally, double rainbows occur when light refracts twice in each water droplets. The second rainbow will appear more faint and it will have its colors inverted. We have come to the end of this chapter. Please share this video with your classmates and follow us on all our social media platforms. Thank you for listening and have a nice day.